Hello everyone. Today we are going to find the electric field due to dipole. Now to calculate the electric field at some position vector r, we will use the machinery of vector calculus. For that, first we will calculate the scalar potential V at position r and then we will take the negative gradient to find the electric field. Now of course, as shown in the figure, we will use the spherical polar coordinates to exploit the azimuthal symmetry around the z-axis. So let us calculate the scalar potential using the superposition principle. So we write potential V at R to be kq upon R plus minus kq upon R minus. Now we can write R plus and R minus using the geometry of the figure, and we will use the cosine law. So using cosine law, R plus square is R square plus D square minus 2RD cos theta, and R minus square is R square plus D square plus 2RD cos theta. Now we make the assumption that the distance r is very greater than the distance between the dipole. Hence using that we can neglect terms of order r 1 upon r square in our calculation. Hence with that r plus will become r 1 minus 2d cos theta upon r raised to half, and r minus will become r 1 plus 2d cos theta upon r raised to half. With this, 1 upon r plus would be 1 upon r one minus 2d cos theta upon r raised to minus half, and 1 upon r minus would be 1 upon r 1 plus 2d cos theta upon r raised to minus half. So let's plug in this r plus and r minus into our scalar potential together with the binomial approximation, which is when x is very small, 1 plus x raised to p can be approximated as 1 plus px. Therefore, v at r would be kq upon r 1 plus 2d cos theta upon 2r minus 1 minus 2d cos theta upon 2r we can simplify this and we'll get kq upon r square 2d cos theta, and remembering the definition of dipole moment, we can simplify this expression further and we can write k p cos theta upon r square, where p is 2qd. Also notice we can write the scalar potential V in a coordinate free notation using this formula k p dot r cap divided by r square. Now we can simply calculate electric field by taking the negative gradient of the scalar potential. So notice we are using spherical polar coordinates, so we express our gradient in spherical polar coordinates and we will get minus dv by dr r cap plus 1 upon r dv by d theta theta cap plus 1 upon r sin theta dv by d phi phi cap, and notice that there is no phi dependence in the potential, so this term goes away and we will get. So let's plug in the expression for V and differentiate it with respect to R and theta, and then we will get the final result for the electric field at position vector R to be 2kp cos theta upon R cube R cap plus kp upon R cube sin theta theta cap. So this is our result. Now let us express this electric field in coordinate free form as well. So that expression would be k upon r cube 3 p dot r cap minus p, where p vector p is magnitude of the p times it points toward the z direction, that's why z cap. Now to see the equivalence of these two equations, let's use the relationship between the unit vectors in spherical polar coordinates and unit vectors in Cartesian coordinates. I have made a video of these relations which uses the elementary trigonometry only, and I will share the link of that video in the description. So remember, I derived the equations where I expressed r cap, theta cap and phi cap in terms of x cap, y cap and z cap, where the matrix was sin theta, cos phi, sin theta, sin phi, cos theta, cos theta, cos phi, cos theta, sin phi, minus sin theta, minus sin phi, cos phi and 0. Also observe that these factors in the matrix are the direction cosines between these unit vectors. That means this is r cap dot x cap, this is r cap dot y cap, this is r cap dot z cap and so on. Theta cap dot x cap, theta cap dot y cap, theta cap dot z cap, phi cap dot z cap, x cap, phi cap dot y cap, phi cap dot z cap. And as this is the direction cosine matrix, it is orthonormal. This is also obvious from the geometry because all we are doing is expressing one set of unit vectors into another set of unit vectors which are rotated in space. That means as it's an orthogonal matrix, we can simply invert it by taking the transpose. And that's why the z cap can be written quite trivially as cos theta r cap minus sin theta theta cap. So let's plug in these expression of z cap into the dipole moment and express the dipole moment in terms of r, in terms of unit vectors r cap, theta cap and phi cap. Therefore, P can be expressed as P cos theta r cap minus P sin theta theta cap. From this now, it's very easy to see the equivalence between those two expressions. So let's start with this equation. E is k upon r cube 3 p dot r cap minus p, and let's plug in this expression into this and we will get k upon r cube 3 times p cos theta r cap minus p sin theta theta cap. This is p dot r cap, so this is p dot r cap times unit vector r cap minus same thing p cos theta r cap minus p sin theta theta cap. Hence, once we simplify this, we will get E at position R will be k upon r cube 2p cos theta r cap plus p sin theta theta cap, and hence those two expressions are equivalent. So let us summarize the entire video now. We first calculated the electric potential using the superposition principle. For that we get the expression Kp cos theta upon r square. Then we took the negative gradient of that and we got the electric field in these spherical polar coordinates. We also saw that we can express this electric field without mentioning any particular coordinate system and write that in a fully vector form.